to the third of our keynotes. So we are traveling around the entire planet for our keynotes, which is one of the joys of this meeting, actually being able to pick people from anywhere on the planet. So a little bit about Mark Quigley, who's our next speaker. So Mark did his PhD at New Mexico and Master of Science in Melbourne, and he was in Toronto for a bachelor's. So he's also traveled around the world, and he's now Associate Professor in Active Tectonics and Geomorphology at the University of Melbourne. On his website, it says that his interest in geology stemmed from a childhood desire to have adventures like Indiana Jones. Perhaps this is Indiana Jones in lockdown, giving a presentation today. So anyway, over to you, Mark.
Thank you very much for the intro, Tim. And hello, everyone. It's a pleasure to have been invited to join you here. It's just after 8 p.m. in Melbourne, and I've just got the kids to bed. I've had my whiskey, and I'm really looking forward to being able to engage with you on the talk I'm about to present. So it was not yet a decade ago that I was in my first academic job at the University of Canterbury in Christchurch, New Zealand, and there was a magnitude 7.1 earthquake 44 kilometers to the west of my property. And at the time I had a big group of PhD students, and so we, by 7 in the morning, we were out in vehicles chasing down the surface rupture. And since then, over the last decade, I've spent much of that time invested at trying to capture the science lessons learned from that event, and increasingly they led me down interesting pathways to places where I perhaps was surprised by the science that was or was not used and how it impacted on the society at large. We did a lot of our work throughout the aftershock sequence, magnitude 6 earthquake in February 22nd in Christchurch, killed 185 people, and then another one in June. I had 11 episodes of liquefaction in my backyard of my house, literally. And so it was a real opportunity to capture this in live through a natural experiment, as it were. So a lot of the science I'm going to present today is from my experience there. However, I would be amiss to say that a lot of the learnings have actually stemmed from work I've been doing with the United Nations Disaster Risk Reduction Office, research that's been funded by the Australian government and the Earthquake Commission, the New Zealand Prime Minister's Science Prizes, and through a lot of work that I've done with industry through GHD, SMEC, Total Energy, and SA Water. So we're going to bring some of the lessons in there. So the talk's about influencing and empowering earthquake risk decisions with observations and models, some of the stuff that we really love to do. Willingness and determination. I think those two things are absolutely critical if we hope to influence and empower. And note that I don't say make earthquake risk decisions, because really we're trying our best to embed our science in a rather complex network of decisions that include multiple inputs, not just science ones. And so I hope you'll get some feeling for that complexity today in the talk. But you know, we have to start here because this is one of the reasons we do what we do, the beauty and the power of earthquake surface ruptures. And so this was a photograph I took from a helicopter of the Darfield earthquake just a day after the rupture had occurred. So I want to talk you through a little bit of the science of earthquakes, just on a real broad brush view. I know that not everybody in the room is an earthquake scientist. This is example of some of the things we do in terms of the surface ruptures. We map these with aerial imagery in the field, with LiDAR, with differential LiDAR now, with terrestrial laser scans, with INSAR, and with a whole plethora of other satellite data, optical satellites and SAR satellites. It's just constantly growing. we take that work that we do, and we some of us are seismologists, so we look at the locations of earthquakes, the focal mechanisms that help us paint the picture of the subsurface rupture geometry and kinematics of the fault systems. The Canterbury earthquake sequence, the Darfield earthquake, and some of the other events were quite complex earthquakes, and that was revealed to us largely from the seismology, although the surface observations were also important. When we take the seismology and we combine it with things like the geodetic data that was available for the area, things like fault zone trap waves, for example, to give us ideas of the seismic velocity of the uppermost 10 kilometers or so, we can paint these quite interesting pictures of the three-dimensional geometry of faults and how much they moved in the earthquake. One of the favorite things that I like to do is to look at LiDAR data in the top left there from New Zealand, and charge around in dense rainforest with a shovel and hand dig some trenches and hopefully find evidence for the last events, the most recent events in terms of their slip and so on. Where a lot of us are using drones now. So this image here shows some of our drone imagery from Central Australia, digging trenches to understand the stratigraphy of faulted sediments there, and some of our surface ruptures from Darfield in the top right here, where we can look at discrete cracks with very clear, measurable, small-scale displacements, trace them into trenches and fill those trenches up with postgraduate students and leave them there for a week or so and see what they come up with, and then go from there. From our trenches, we make maps of these events. We can hopefully date events through that. We can look at probability density distributions of multiple events, just get some idea of the timing of earthquakes on those fault systems, combine those with various other measures of offsets and rupture lengths to look at the moment magnitudes of those earthquakes. Look at multiple cumulative discrete displacements. So here it's showing dextral displacement for events along the Hope Fault in New Zealand, and calculate mean single event displacements summed up over multiple events is commonplace. And look at slip rates through time. So where we have a long record of multiple earthquakes, we can see how they depart from, say, a steady state rate that we might otherwise determine from just a measurement of a single offset that accumulated multiple events. And so these all fit together into what we consider to be the fault source inputs into regional seismic hazard models. So just an example of how we might construct a seismic hazard model. We have our background sources, our seismicity sources, and then we have our fault sources, and that's the particular field of expertise that I'm most interested in. We combine those two things, seismicity and faults, with things like ground motion prediction equations shown in the bottom left here, which tell us something about spectral accelerations or intensities of ground motions as a function of distance from the sources. Mix those around and we end up with maps of seismic hazard over various time scales and in spatial scales. And so this is an example of the central South Island of New Zealand, showing the 500-year shallow soil peak ground accelerations and gravity, nicely illuminating the Alpine Fault and Hope Fault system, which runs through the South Island there. The site of the Kaikoura earthquake is shown up quite clear in yellow and red there. These sort of things can be broken apart for any location. And so for Christchurch on the east coast of the South Island here, you can look at, for different intensities of shaking, what the expected return period of that shaking might be, the black dashed line here, in hundreds or thousands of years, and the breakdown of all the sources that are perhaps most predominant in contributing to that shaking. And so when we get up into the intensities of shaking that we felt in Christchurch during the 2011 event, the sort of 8s and 9s, we can see that the expected return times of that level of shaking are on the orders of 5 to 10,000 years. and the predominant percentage of hazard contributed to in those sort of events expected from models prior to the earthquake was from background seismicity. In other words, faults we don't know about, magnitude 6s or 6.5s beneath the city. I think it's often easy to forget that when an event actually like this occurs, the media is quick to jump on how surprising it was and how the scientists were unprepared for such an event. But these models were all done before the Canterbury earthquake sequence, and I think they highlight that while this was an area of comparably low seismic hazard relative to other parts of the South Island, it is an area where local sources contributed the highest amount of hazard, and where if we build out into longer timescales, 0.5, 0.6 Gs are not unexpected. It's this kind of information that goes together to inform things like the building codes, and we'll get into that in a bit more in a second. Here's an example of the New Zealand seismic hazard map on the left here, the Italian seismic hazard map in the center, and the Australian one on the right. And basically these are maps that show the two on the left, a 10% probability of PGA exceedance in 50 years. Various levels, they help you look at relative hazard throughout these regions. The spine, central spine of Italy there showing up in red, and the main fault systems on shore on the South Island showing up in red there. In Australia, this sort of clustered, spotty places of comparably high and low hazard. Obviously, on a global sense, these areas are very low hazard, but they allow us to hopefully sort of manage, micro-zone our hazard in continents. So all of this context, all of this interesting and fascinating work that we all love feeds into, I suppose, the misconception that the work could be done at this stage, that we've done all we can. And so this is a rather famous quote, which I haven't directly attributed, but you can quickly find the source if you want to. In publishing an official map, seismologists have done all they can to protect society from earthquakes. I can hardly be blamed for the poor quality of building or for people's failure to conform to anti-seismic laws. These are the responsibility of other authorities. There are many other outspoken voices about the role of science. Science advisory boards should stick out a policy and stick to science. And this kind of conception that if only the decision makers understood science the way I understand it, then they would share my values, surely, and the decisions that they would make would align with prevailing science evidence. And in speaking to a UK audience at the moment, I'm sure a lot of you might chuckle about that particular statement, given the coronavirus various comings and goings, but I don't want to venture into that territory at the moment. One of the things about seismic hazard, of course, is it can change very, very quickly and dramatically. And so this is an image of the decade of seismicity in the Christchurch region prior to the Darfield earthquake. There was a sequence in the mid-90s, and in between 2000 and 2010, there were still some aftershocks, perhaps, in those particular areas, as well as some local events. But how quickly things change. And so these are magnitude 3 earthquakes or greater in that next 2.5 years, just basically swamping the city of Christchurch. Embedded within that, all these events going on. You can see several state of emergencies at the top of the screen there, land use decisions being made, zoning reviews, offers to buy people's homes so that they can move on with their lives, district plannings, and so on. And science was feeding into a lot of these types of decisions throughout events that cause surface rupture, liquefaction and rockfall of varying severity, cliff collapse events of various severity. I don't need to say that in an earthquake sequence like this, this is something that you never abandon. It lives with you forever. And when you're having magnitude, we had 4,000 magnitude 3s, it feels like the ground is almost constantly shaking. So to deal with this kind of issue, we look at seismic hazard on a variety of shorter timescales. And Operational earthquake forecasting is something that is done increasingly more. It was really the big first rollout of that in 2010 in New Zealand. And it allows you, like a weather forecast, I suppose, to look at various short-term forecasts of your chances of feeling strong shaking. 24-hour aftershock forecast maps, month-long probability forecasts to yearly probability forecasts. The variety of models contribute to this. You might have heard of some of these: EPAS, ETAS, STEP, and their various offsprings and hybrids and so on. One thing that's really important about all this work is that these probabilities are highly contextual, and so there's a tendency for some people in the public to say, oh, okay, there's only a 45% chance of a magnitude 5.8 earthquake happening in this region in the next year. Perhaps that's less than half. But as earthquake scientists, if we thought that there was a 50% chance of something large and damaging occurring in our city, we would be blown away by that probability. And so communicating to people that relative change in hazard and how it relates to risk was rather quite important. I think we're moving in seismic hazard, in particular in the short-term space, into trying to integrate physics-based models that sort of encompass a variety of potential sources. I know that we've been using physics-based models for a long time, but one of the things we're trying to do now in Australia and New Zealand is look at multiple source models, multiple receiver fault geometries, multiple slip models, and so on, to try to understand what effects they might have on, for example, the state of stress on potential receiver faults, the relative stress, Coulomb stress change, and how these things basically allow us to forecast the distributions of seismicity. So not just the rates like the operational earthquake forecasting models, but actually guiding us a little bit more into the space of locations. And so I think that this work is incredibly important. I love doing it. Often we come up with results like I'm showing down here, where you take a simple model and produce a simple fault model, produce a Coulomb model, and then take a complex one that might be closer to reality, and it gives you the same kind of answer. And so I know multiple people have found this. It's important to make our models as good as we can, but sometimes simplicity is important as well. I'm going to add to this that the verifiable lives, record of lives saved by this kind of stuff, and of physics-based rupture forecasts, so operational earthquake forecast models and physics-based models, is virtually non-existent. I think a lot of time the results are too ambiguous to group evacuate a city, for example. How do we know, just because we have a 1 megapascal increase on a potential receiver fault somewhere, that earthquake is going to occur on the sort of time scale that might allow us to go away for the weekend and come back when it's all over. I think often they're too short-term also to strengthen major structures, so to kind of go around and retrofit buildings before the big aftershock occurs. I think they have an emerging role in building code revisions. So, for example, in Christchurch, certainly there were a lot of discussions about revising the building code in light of the ongoing seismicity and in some of the results from some of the models that were being produced. Perhaps from the perspective of land use planning decisions, they're quite important as well. And I'm going to show you an example of that in a second. I think the other thing that's kind of interesting for me is this idea of nudge theory, where you're kind of trying to nudge personal decision making at a local level. And you might laugh at this, but certainly we all know that the most dangerous time to have a strong earthquake is immediately after you've just had one. So taking a seismic holiday where you go visit the grandparents 2 hours away for a week, or perhaps thinking about putting a few bolts into that bookshelf that you always kind of wondered about, or perhaps moving your television to a different location so it's not going to topple over on your toddler. These are the kind of nudging that we hope to bring in by discussing these results. So into decision making, and really, we've talked about a whole bunch of kind of snippets of science and how it might inform decision making. The important thing is this is an incredibly complex field of research, and so we might have a whole variety of end users, including our fellow scientists that might use seismic hazard models to go and find places to do more research. Governments at all scales and hazards analysts, planners, industries of all types, including the insurance industry. I do a lot of work with asset owners, for example, owners of dams or tunnels or so on. Citizens, of course, in ways I've just spoke of. So decision makers of all type. The type of decisions can be things like, should we revise our building code? How do we do land use planning and consents? Fault zone avoidance, for example. Engineering design criteria, and plannings for all type of infrastructure, emergency management and evacuations. The type of questions that are typically asked for a lot of industry and infrastructure is, what is the anticipated seismic loading and spectral accelerations or peak ground accelerations that we might expect for a given structure in a certain area over a specified period of interest? And that might be 1 year or 500 years or 2,500 years for more important infrastructure. And how exposed are the structures, like, for example, the dam that I'm showing here, to fault zones? And what is the probability of exceedance of specified fault displacements over relevant timescales? And so we're typically doing the kind of things I mentioned earlier, digging trenches, studying the faults, the stuff we love to do, and then doing things like probabilistic fault displacement hazard analyses, where we essentially try to embed a risk approach into the looking at the amount of displacement that might occur on a trace in close proximity or even right underneath areas of critical infrastructure. So you have a displacement here, it goes in a logarithmic scale, so on the order of sort of 4 to 5 meters, you might have a 1% probability in 50 years based on paleoseismic trenching and integration of that into this kind of work. I think we would be amiss to not state that our moments commonly emerge during crises. And so for me, that was certainly the case, from a lecturer somewhat naive about the role of science and all this stuff, to within days talking to the Prime Minister at the time, wandering around sites of devastation, destruction, being asked like questions: should we rebuild or abandon fault zones? What do we do in areas of liquefaction hazard? What do we do in areas where we had mass movement hazard? So we've got an rather expensive modern house that was obviously built quite close to a cliff face in the first place, and then one built right at the very bottom of that. And I guess one thing I learned is that these are rather simple questions, but with very complex answers, where science is an input, but not the only input. Let's move quickly into risk, because it's important we're on the same page for this aspect, and then I'll talk you through some things that'll give you a little bit of work to do. You might be asked as a hazards analyst, as a earth scientist, to try to give estimates of the annual individual fatality risk from an earthquake-triggered rockfall in a certain area. That's a kind of risk that we might be really quite interested in knowing during an ongoing aftershock sequence. And that risk could be computed by, for example, thinking about the annual probability of such an event occurring. That would obviously decay in time with an aftershock sequence, with the highest risk basically in the shortest term, and a decay. It would also obviously relate to the susceptibility of rock masses to having rockfall events if seismic loading is imposed upon them. And so this plot just shows basically peak ground velocities on the y-axis, epicentral distance on the x, and a variety of earthquakes that caused varying amounts of rockfall flux. And so you can kind of establish criteria, thresholds, if I may, for various rock faces, and embed that into that scenario. The next metric is a probability of a person being in the path of one of the boulders that would potentially come down. And so to do that, of course, we have the reality that rocks did come down and go through people's houses and kill people. And so we know that that is a future risk as well. And we can model trajectories of rockfall boulders, both empirically, ones that have already occurred, and also potentially future events. The probability that a person is present at that location when the event occurs, that largely relates to how they run their time. That's an exposure metric. Are they at work most of the day and they just come home for the nighttime? Is it a beach house that they only visit for one day a year or a couple days a year? These are the kind of things we're interested in there. And then the vulnerability, the probability of a person being killed if they're hit by the rocks. So what sort of structures might be able to withstand falling rocks, for example? These risk maps that get produced here can be displayed like this one, where you have the annual individual fatality colors here for different metrics. Individual boulders mapped in red, and I think that's the critical aspect of science, the contribution of science there. But then what we do with this information as a society is really quite interesting, and that's where we have sort of questionable roles. Where do they finish? And so we have science evidence, we have science advice that we might give pertaining to things like uncertainties and future forecasts and so on. We have variations in societal risk perceptions and thresholds. Some people would say, well, you know, my risk of dying in a rockfall is 1 in 1,000 or 1 in 10,000 in the next year. But for me, you know, I'm a thrill seeker. I'm an adventurist. You know, a lot of the other things I do have similar risk thresholds. I'm a heavy smoker, etc. And so weaving science into that narrative is quite interesting. What do we do about divergent evidence? You know, where where some science points one way and points the other. How do we characterize uncertainty, and how does that all embed into decision making? And so some thoughts from some leaders on this particular aspect. Scientists are citizens, and as experts, we have an important role to play in public debates. We advocate for things. Science advice is not generally a matter of dealing with early issues that need technical solutions. It's sought in dealing with sensitive matters of high public concern and inevitably associated with uncertainty and scientific and political complexity. Scientists have social responsibilities to the larger community. It's no longer acceptable to focus on our internal responsibilities. And something from a paper on the L'Aquila earthquake that I really quite enjoyed. Contradictions, controversy, and conflicts are bound to arise in the practice of expert advice for public policy as a result of the improper reduction of the overall situation uncertainty to its scientific component only. The treatment and communication of scientific uncertainty is an independent variable that can be analyzed and computed in isolation from other concerns. I think a lot of this puts us into a rather uncomfortable place, but an important place. So I've got some exercises for you here. The first one is that a magnitude 7 earthquake occurs 40 kilometers away from where you live. You're experiencing strong aftershocks all the time. You live across the road from a vacant site at the edge of a steep cliff face. You notice that during this aftershock sequence, for some reason, 6 townhouses are built right in that area. This is not just a science question, it's a question that transcends science. But is there a way that you can sort of cast your mind to things that could be done? Is this a nudging question? It turns out that this was quite a bad decision to make in terms of going ahead with this. Lots of rocks came down throughout the earthquake sequence. Houses immediately above were shattered to bits. And so this is one of these things where perhaps having a strong voice in the media, for example, about the importance of, the high hazard going forward, and perhaps slowing down decisions regarding of this type while this is going on would be one way to play that. This is another example. You're in a helicopter and you see a tension crack forming at the top of a steep cliff in an urban suburb. Obviously, there's an obligation there, a duty to communicate about the potential for that thing to fail in subsequent earthquakes, which it did just a few months after that photograph was taken. Okay, this one here is another example. You have modern rockfall boulders that came down into this populated area here. Some of them went through houses and so on. You go out to that landscape and you notice that there are thousands of rocks that were there before. a lot of them, the maximum limit in which and how far they have traveled is significantly shorter. In fact, it's higher up the hill slope, meaning that those thousands of rocks that we see in the landscape, none of them actually made it into that village. You go and date those things, and you find that there has been no major rockfall events in the last sort of 5 to 6 or 7,000 years. And when you make models to try to explain your age distribution, you sort of get this periodic model of 7,000-year rockfall events separated by long periods of quiescence to be the model that you think is most suitable to explain your data. You then excavate around the sides of boulders to do independent tests on those and find that the sediment that backs up in behind the boulders, so the sediment that was deposited after the boulders was in place, is up to 7,000 years old, and that the boulders lie on a surface that's some 12,000 years old, all giving you kind of the idea that this is a rather rare extreme event that has occurred here. You put this into a model and you realize that actually when those ancient rockfalls occurred, the area was completely vegetated with native forest. And so it's quite likely when you run your numerical models of the boulders that that native forest actually stopped those boulders from going down into this particular area, which subsequently was inhabited. And so this deforestation, in a sense, enabled these rocks to travel into the village. It increased the life safety risk, perhaps inadvertently. So you have this relevant science. You have a willingness and a determination to contribute that, but you have no clear pathway to the decision-making table. So you know that things are being done in there, but you don't know how to get a voice. And this is an example of how you could perhaps use media leveraging. So when we did all these studies, we actually ran a story in the local newspaper. There were some residents nearby that were being affected by these sorts of decisions that wanted to understand our science and use it in court cases that were ongoing. And so there was a stakeholder solicitation of this science that was previously not being considered, not at the table. And with that, we had a rather pragmatic view of how this research might ultimately influence decision-making. Certainly, it favored a less precautionary approach, and that in turn made us very, very nervous. So how does science contribute to a decision-making process? You can think about it as linear. It's not entirely linear, but there are some linear elements. And so what's happening here is there's a series of questions like, did rockfalls occur at those sites? Yes or no? We can contribute to that through our surveys and so on. Is future seismic and rockfall activity likely? Yes or no? Yes, it probably is, given the ongoing seismicity and so on. Does future rockfall pose an unacceptable risk to life? Well, it poses a high risk to life, and if society deems that to be unacceptable, then the answer to that could very well be yes. And then finally, can we mitigate that through protective works? And is that feasible? Does it create a large disruption to landowners, timeless and cost effectiveness? If we can't mitigate it in a way that makes sense for society, then ultimately it may be time to abandon that area, to make purchases of those properties and move people on. So when I contributed this advice, and I can't go into it in much more detail, but I will say that it was a fascinating process, that the decision makers were satisfied, that my research was not a basis for taking a less cautious approach, that it was of assistance, and that it supported a regime that would allow those hazard lines to be adjusted when more information becomes available. Similar types of processes were involved in liquefaction. So was the land damage at the site significant and extensive? Is it likely there'll be more? Can we remediate? Are they likely to be successful? And would that proposed engineering solutions be disruptive and protracted? And so ultimately, if the science points to high risk and the economics and the engineering solutions suggest that it's going to be quite disruptive and may or may not even work, then ultimately the decisions might be made. I think one of the interesting things that we also learn about science is that sometimes decision makers give us the impression that the science, the actual nuts and bolts, the evidence is the thing that is underpinning the decision, when in reality it may be the economic inputs that are deciding the actual ultimate trajectory of decisions. And so what I'm showing here is that it came out about a year after the public documents were released about the kind of decision making, that actually the decisions were made based on cost. So there was a contribution from the national insurer, plus a betterment cost that would be required to raise the land and perhaps reduce it to future risks, plus an infrastructural cost, replacing all the broken water mains and sewage pipes and all the rest of it. And if that cost of all that stuff was greater than the actual value of the land in 2007, then it was red zoned. And if all those costs were less, then it might have been green zoned and with remediation. I found that quite interesting because it's that classic science meets economics, that kind of COVID problem, if we want to call it that. Ultimately, a lot of the red zone decisions that were made were based on science advice. The evidence was the detailed evidence was often collected after and kind of backfilled the policy. And that was because they had to make decisions quickly to give people certainty. There were perhaps some elements of an inaccurate portrayal of science. We can call that the L'Aquila problem. And then there's a whole issue of what next when something like this happens. So in my backyard, for example, we had this multiple liquefaction events. And obviously, I was in a position as a geologist to do something about this. So I got an excavator to come to my house and dig some big holes. And I did some paleoliquefaction studies and found that liquefaction had occurred before below my house. And so in this context of what do we do with this giant $1 billion worth of land that's been temporarily red zoned going forward, when can we put houses back onto that? I think I was put into a position where I could perhaps try to extend beyond my science and offer perspectives. And I think when we think about this kind of aspect of how we engage, it's useful for us to think about how we might be acting. Are we acting as a pure scientist who's just sticking to the science and nothing more? Are we aiming to try to provide answers to questions that are rooted in science in a sort of linear model? We're being asked by decision makers with concentrated power, can you please answer these questions for us? And we might be able to do that. Are we going to advocate for choices amongst the variety of different options that might be available, or actually help clarify the scope of possible actions to empower the decision makers? And in a sense, I tried to act in all those fronts, carefully, mind you, but from just communicating things to the general public about what we know about the earthquake and so on, to advocating for further work that should be done before we rebuild, to sort of posing alternative solutions that could be put into the public sphere for discussion and debate. And so I think it's critical that we try to expand our horizons beyond that. This is an incredibly complicated dialogue and a diagram, and it's a good thing it's in Slack, so you can look at it in detail if you want. But disaster science is very time compressed and very messy. And what this is intended to show here, so for example, a fault rupture response, is that we deploy teams immediately, we do press releases and we map the ruptures. Decisions start to be made before we've actually finished publishing our research on the ruptures. Other people are, other decision makers are making decisions for which our paleoseismic work could be relevant before we're actually able to get the paleoseismic work done. Often paleoseismology is at a disadvantage because it takes longer, you're waiting on dating and so on. Decision makers want to be certain and they want to make decisions expediently and so on. And so this is really a diagram to try to help you understand how we might document the variety of things that are going on and how our science fits into it. It's a way of kind of reducing our naivety in some senses. Some things we've learned from this kind of thing: pre-disaster geotechnical guidelines and diverse collaboration networks enhance our ability to meet the expedient demands of decision makers. Often there are scientists that are obliged to respond, to collect local data, to just to basically contribute that directly to decision makers. We need to have diverse teams so that some can focus on publishing science in the whiz-bang journals, while others focus on the policy deliveries and the communications, and some of us try to do it all. Expedient requirements often require reliance on expert advice rather than detailed evidence, particularly if precautionary approaches are favored. And so it may be that doing some things quickly that help to, in a reconnaissance way, to help us be able to contribute to decision-making discussions rapidly is ultimately going to be the thing that is most influential. Pre-disaster paleoseismology is going to have a greater influence, potential to influence decision-making than post. There often just isn't time. And that makes me a bit sad because that's what I love to do. But the reality is that often doesn't happen. Okay, I'm going to finish now with a little bit of science, a bit of fun stuff. I think in terms of seismic hazard, some of the things that we're working on now is multifold earthquakes. So it's a real kind of bandwagon at the moment. A lot of people are really interested in this, and so we're looking at things like in Darfield earthquake, there were 7 faults that ruptured in that rupture cascade. We did Coulomb stress modeling, starting the earthquakes on different source faults and seeing how they basically enhance stresses across the network. We did things like do slip tendency analysis of the faults. So some of the faults, for example, in this region had high slip tendency. Others had very low slip tendency, including the fault that the earthquake actually initiated on. And so what these results are telling us is that in some places, the multifold earthquakes are much more likely, probabilistically, than ruptures limited to single source faults. And so what that means is the typical seismic hazard approach of just saying, well, here's the size of your source. It can generate a magnitude 6.5 or 6 or whatever. If we look at our analyses, we say, actually, most of these scenarios cascade across the entire network and generate 7.1s. And I think that that's something that we need to think about in the context of seismic hazard. Another thing I think that I found really quite interesting at the moment is where faults intersect. We often think about these as sort of having parabolic slip distributions and being at the termini of faults where slip would be at a minimum. But as we look at some of these Australian earthquakes, for example, the slip maxima are actually occurring. The black line here, this is slip and length. The slip maxima are actually occurring where orthogonal fault sets are interacting. And not only the peak displacements occurring there, but we're also getting a lot of the highest topographic noise there. In other words, the greatest variability in our individual slips, the noisiness of the rupture when we look at the high frequency signal. And so it's telling us that these junctions are rather important parts of seismic hazard, and that helps us to communicate to perhaps decision makers that have infrastructure at the intersection zones of faults that they may not expect zero slip as the faults taper, but that may actually have a maximum there. The other thing I think is really interesting is the role of crustal structure in influencing seismic displacements. We find for the Petermann earthquake, and you've got your local resident expert, Tamara King there, who knows more about this than I do, but the Petermann earthquake erupted along this really heterogeneous bedrock structures there, which allowed it to have a long and rather smooth surface rupture profile, where we have other earthquakes that have actually terminated against geophysical anomalies with very noisy rupture profiles and so on. So there's a source of not really exploited to its full extent crustal structure involved in that. And finally, advancing seismic hazard through other strong ground motion proxies. I love this stuff, looking at liquefaction, the stratigraphy of sand blows, looking at rocks and boulders that have been shaken around in their sockets where other soil has come in, or fragmented or dislodged, looking at boulders that have been displaced in directions that are actually where we have nearby instrumental records show the same sort of polarity. So they're telling us about strong shaking. And then things like using trees. I mean, there's the obvious ones right on the fault, which is always fantastic, but also trees damaged by rockfall, trees submerged by co-seismic subsidence, all these sort of proxies. We got fragile rock geological features, and all of these things can help us to better understand and characterize seismic hazard. And finally, some encouragement to the community. When I've got this nice audience, I'd like to put myself in a position of advocating for this. I think as a community, we need to try to better document, to analyze, and to share our experience of how our science did or did not inform decision making, and why or why not. What the other relevance inputs were, be they economic, be they some other social things that were prioritized, and what we could do better. I think it's important that we kind of buy into this a little bit as a community, because we all have a range of contexts, societal needs, priorities. We're all different, so we have different value judgments, sometimes even amongst our community. We're trying to talk to different decision makers about different problems. And I would never ask you to do something I wouldn't do myself. And so I've given you some examples of our research in this space, where we've really tried to capture all of the great detail, what science was communicated to whom, what they did with it or didn't do with it, and why, and how we can learn from that. So I've gone over time for sure. Perhaps I should have had one less whiskey this evening, but thank you very much for your attention, and I'll look forward to questions.
Thank you, Mark. That's a fantastic overview of a huge number of things. So we are at the end of the scheduled session, but we'll take 5 minutes of discussion and then pass everything else onto Slack, or where I think you may either respond later tonight or tomorrow, more likely, I think.
No, I can respond tonight. That's okay.
Brilliant. So maybe I'll kick off. I mean, you talked about that balance between individuals doing the science and people doing the kind of communication hazard specialist. You know, what's the kind of ideal situation for a team, and what would your advice be to young scientists coming into this area, in terms of how much should they focus on really becoming experts on the science, or how much should they try and spread themselves across both the science and the communication and the risk areas that you've also talked about?
Yeah, thanks, Tim. That's a nice question. So I was a young scientist when this event happened. I'm not as young anymore. Possibly the two things are even related, but the things that I found the biggest voids at that time were the ability to clearly articulate the science to the general public as someone who was in the front line of the science, and so someone who could share the experience of doing science as it was happening. And I think we have roles to play where we don't view science as an end product that we communicate to the general public once our Nature paper is published and everything's all done and dusted, but that we communicate throughout the scientific process. And so I think for young people who find themselves in a position where they have the ability to communicate throughout and show the public and the decision makers the joy and the beauty and the honesty and the transparency of science, I think that's a wonderful thing to prioritize. Other things, I think strategic partnerships with local scientists are fantastic, and I'd always advocate for that. And not just local universities, but local government scientists, people that are obligated to respond and who have these really important local roles. So for me, partnering up with my colleagues at GNS Science was a tremendous learning experience. It allowed me to sort of engage with the way they do science. It allowed me to extend my reach into decision makers and so on. And diversified that. But why I say it's important to have a diverse group, I think, is because you can't do it all. You can try, but I think just having a group that people have different priorities. Some people want to publish the top-notch paper, while others want to do the sort of the grassroots communication and so on. I think it's wonderful to have a coherent team beforehand that can kind of just nail it on all regards. And so seeking out those kind of collaborations is a great thing I would advocate for.
Great. Another couple of questions, and then we'll let people have a lunch break. So Laura Gregory asks, what do you think of the case where the underlying science is wrong, or there are very contrasting views that can't be reconciled? but may be important for making those decisions.
Yeah, so it's all about uncertainty and how we address that, how we tackle that as a community, how we convert epistemic uncertainty into sort of statistical uncertainties that we can use to capture the range of potential outcomes. And I think if we think about things like structured expert elicitation, I think being on the front foot and engaging with. Hello, are you still there?
I think I've frozen a little bit there, but I've just come back. So I didn't hear your answer, but I'm sure it was a good one.
That's okay.
There's a final question from Camilla.
No, I'll just finish up.
Okay, sorry.
Okay.
Carry on.
Yeah, so just to top that up, engaging with pseudoscience and providing an evidence-based sort of counter to that is really, really critical. And I think there's also times when, for example, operational time, when decision makers need the right decision, be it precautionary or whatever. They don't want to hear a bunch of scientists arguing about whether you should or shouldn't evacuate from a flood zone when the flood's coming, for example. There are times to engage in scientific debate, even publicly, and other times when it's perhaps best to have a unified front when it's quite clear that a precautionary approach is needed. So yeah, and there was a final question, Tim.
Yeah, great. And then we'll pass on. I know there's a few more as well that we'll pass into Slack. So Camilla Penny asks about, says we're still clearly learning a lot about what hazard actually looks like. Making a map is clearly not enough, but does making a PSHA map imply a level of certainty to a decision maker, which we don't actually have? Thinking of, for example, it being unclear whether return periods really make sense for some of the Australian earthquakes.
Yeah, well, I can say, the New Zealand seismic hazard map, that, and a lot of these maps, they're not actually wrong. The events are often low. When low probability of events occur, it doesn't mean that the seismic hazard map was wrong. It just means that a low probability event occurred. I think where these things kind of fall down when people look at them and then they say, well, how did we get 185 fatalities? And that is not to do with the maps or even the building codes. Often there are things like legacy issues with buildings. There may be flawed building designs. There may be corruption in the industry and so on that influence those sorts of things. And so perhaps there's some deeper elements that I could discuss in the Slack, but I would say that I think it's about model ensembles. I think it's about basically saying here are a variety of different types of models that all kind of tell us the same thing, more or less. And so we need to adjust accordingly. And also, why are we shooting for a minimum standard of buildings? The code tells us this, so we're going to build it at the minimum standard so that they don't collapse and kill people, but we still have to sink billions of dollars into the rebuild when we could actually just spend a little bit more and make the building stronger to begin with. There's a lot of deep questions there that I'd be happy to discuss more.
Great, thank you, Mark. And so I look forward to further discussions in Slack, either during lunch or later on in the day. And let's just turn our videos on and give Mark a kind of clap so you can actually see some real faces. So thank you for joining us late in the evening. So.